Hello everyone. In this video we are going to look at what I call a traditional standard short answer question from the AP Physics 1 exam. This one is from 2015 and I'm going to look at problem number 1. Alright, so notice here in the directions it says that question 1 is an example of a short free response question. Okay, so we have a picture here, and it says two blocks are connected by a string of negligible mass that passes over massless pulleys that turn with negligible friction, as shown above. Mass 2 is greater than mass 1. The blocks are released from rest. So if the blocks are going to be released from rest, once I let go of them, I expect the entire system to move this way and go down because M2 has a greater mass. All right, letter A. The dots below represent the two blocks. Draw free body diagrams showing and labeling the forces exerted on each block. Draw the relative lengths of all vectors to reflect the relative magnitudes of all forces. So there's always going to be a question like this where they take the two blocks and they turn them into a dot. So I'll put a dot there, I'll put a dot there, and I'm now supposed to draw the free body diagrams with the forces that are coming off those dots. So here is block 2, there's the dot. And since mass 2 has a greater mass, I'm going to draw a longer arrow, and we're going to label that arrow FW. You could call it FW, or you could call it FG. Or I'm going to instead call it MG, so that I can put the 2 there to differentiate between mass 1. Mass 1 has a smaller mass, which means its FW arrow would be shorter. I really don't know how long to draw these. All they're looking at is that your arrow for block 2 is longer than block 1. And by having these reference lines there, that's how they can correct the exam very easily. So sometimes I label a downward arrow FW, sometimes I label it FG, but again, in this case, I think it's probably better to call it MG and make that that's M1, M1G. All right, so the blocks are not on a table, so there's no normal force going upward, but there is, each block is attached to a piece of string. And so a piece of string has tension. So Ft is what I should use to describe the tension. I know that this block is going down. It's pulling the whole system downward. So I know that this arrow has to be longer than the Ft arrow. So again, that's what those reference lines let the reader or the corrector know. And since this is the same piece of string that goes all the way across, and because they said that those pulleys were massless and frictionless, it kind of means like the pulleys are invisible. And so that's the same piece of string, which means that the tension in this string has to be the same as the tension in this string, which means that the length that I draw it has to be the same. But now I have to clean this up a bit. If this is the tension here and this is the tension here, this block is going upward, which means that this arrow has to be longer than this arrow, which means I'm going to shorten this guy up and make it something like that. So that's what they mean by drawing a free body diagram and labeling it and making sure that everything is proportional. And that's what the reference lines are there to show me. All right, question B, derive There's a task verb. Derive the magnitude of the acceleration of block 2. Express your answers in terms of, which means the answer can only have those variables in it. All right, the word derive means that I have to start with an equation and show logical steps. So how would I know what equation to start with? Well, the equation depends on the picture. So I'm just going to redraw this very quickly. So over here, this is M1. We have FT, and then we had a short M1G. And over here for M2, since the system is going downward, we had a big M2G, and then we have to have the same height tension over here, but it's got to be shorter than this. So this is showing that the system is going this way. All right, so this is what the word derive means. It means start with an equation, a basic equation that comes from the equation sheet that they give you. So I'm going to write down F net equals MA. So I'm applying this equation to this picture, and I'm going to apply the same equation to this picture. All right, so what would be the net force in this picture? So the net force is always the big arrow minus the little arrow. So it's going to be Ft minus M1G equals M. M is the mass of whatever's in this picture. That's M1A. So this is a derivation. You start with an equation and then you do something logical. Same thing over here. Big arrow, that would be M2G minus the little arrow equals MA. But the mass of this dot is M2. Since M1 and M2 are tied together by this piece of string, that means like they're moving like a train. And if they're moving connected to each other, their accelerations are the same. So the acceleration of M1 and the acceleration of M2 is the exact same thing. All right, so I'm trying to find the acceleration. So when I look at this, my answers can have an M1, an M2, and a G in it, but they can't have an FT in it. And each of my equations has an FT, which tells me I have to get rid of FT. So to get rid of FT, we're going to solve for FT and then substitute it in the other equation. So here I'm going to say that FT, again, remember derivation is to show a bunch of logical steps. All right, let's add an M1G to both sides. So that's going to give me M1A plus M1G. All right, that's good. Now I'm going to take this equation and let's kind of write it down here. All right, so I'm going to write down M2G. Whoops, I'm going off the paper. Okay, M2G minus FT minus FT. I'm going to plug in this whole quantity now. So M1A plus M1G equals M2A equals M2A. Derivations are nice and logical. So I'm going to take this and I'm now going to distribute that negative sign. So M1A minus M1G equals M2A. I'm supposed to be solving for A. I have an A here and I have an A here. So I'm going to move this to the other side. So that would leave me over here an M2G minus an M1G, and then over here I have M2A, but I'm moving this over, so I'm adding it to both sides. So plus M1A. So over here we have M2G minus M1G. And I'm supposed to be solving for A, so how about we factor out the A? That would give me M2 plus M1. And so if I divide M1 or M2 plus M1 on both sides, so that would cancel this, and I'll move it over here. M2 plus M1 equals A. Oh, then always do a check. Derive the magnitude of the acceleration of block 2. That is the acceleration of block 2. It's also the acceleration of block 1. They were trying to trick us. And express your answers in terms of M1, M2, G. I have M1s, I have M2s, and I have a G. So that's good. That's good. That's what I would call a typical short answer question. All right, but let's continue. It continues here. So I'm going on to the next page. All right, so notice this first picture had just the 2 hanging blocks, and the whole system was going this way. Now we are adding a block 3. Block 3 of mass 3 is added to the system as shown below. There is no friction between block 3 and the table. All right, indicate whether the magnitude of the acceleration of block 2 is now larger, smaller, or the same as the original 2-block system. So let me just sketch the 2-block system here for a minute. So if I look at this, when you have a system, when you have things that are connected, so I'm going to write F net equals MA. But when you have things that are connected, this M becomes the net mass. So this net mass would be the mass. So F net becomes like what moves this system. What moves this system is this heavy mass. So I'm going to call that M2G. And then what is this heavy mass moving? Like if he was the engine of the train, what would he be pulling? Well, he would be pulling mass 1 plus mass 2. And then the acceleration, which I won't write it down, but the acceleration is equal to this. All right, but now we have this third mass in here. So now, what is pulling this train? Well, this heavy block is still pulling that train. So that's going to be M2G. But now the net mass, what is it pulling? It's pulling all 3 masses. It's pulling mass 1 plus mass 2 plus mass 3. And it's going to cause it to accelerate. So the question is this acceleration larger, smaller, or the same as this acceleration? Well, quite simply, and they don't want you to recalculate it, they want you to say that you have increased this mass. So if this mass is getting bigger, this acceleration has to become smaller because it's being pulled with the same force of that hanging block. Let me say that again since that was off screen. Since I added an additional mass, the mass here is getting bigger, which means the acceleration has to be getting smaller. That's just showing the relationship between F equals MA. So that is the end of this problem, and this is an example of what I call a traditional physics problem. But even though it's a traditional problem, did you notice that there's no numbers in the problem? It's all variables. That is very common. Sometimes there'll be a mathematical answer, but many times the answer is going to be all in terms of variables. But this would be a typical short answer problem solving question. All right, we'll end this video and we'll do another example in the next one.